So let's do another mass spring problem. These are really just straightforward plugins. Now that we have all the equations, let's say I have a mass on a spring. Spring has a spring constant 20 newtons per meter. Mass is 2 kilograms. We stretch the spring 20 centimeters from equilibrium and let it go. I don't know why I chose all numbers with 2's, but it doesn't matter. This would be like a typical spring in the lab. 20 newtons per meter is sort of is not real soft, but it's it's a typical spring you might pull out of a drawer. 2 kilograms, that's like a 2-liter bottle, right? A 2-liter bottle. We hang that 2-liter bottle from a spring, we stretch it 20 centimeters from equilibrium, let it oscillate, and ask what's the fastest speed, what's the maximum speed? Well, so it is pretty much just a plug-in. I asked what is the maximum speed. Sorry, I don't know if I asked that before. That's what the question I meant to ask. Let's go ahead and write it down. There we go. And let's go ahead and change color to write the answer. It is just referring to the equations. We can start from the basis, or we can just go right to, we know that V equals A omega times the cosine of omega t plus phi, and A, therefore V max, we could have gone right to this, is equal to A omega, because the maximum of the cosine is that, which is A times the square root of K over M. So it's a very straightforward plug-in. 0.2 meters, just make sure you get your units right, times the square root of K, 20 newtons per meter over M, 2 kilograms. Go ahead and check those units, that the Newton per meter is a kilogram per second squared. So this ends up giving us, the square root ends up giving us underneath the square root is 1 over second squared. So it gives us the square root of 10, 1 over seconds. And so we've got 0.2 times the square root of 10 meters per second. Go ahead and plug that in, and that is 0.63 meters per second. That's the maximum speed of the mass during an oscillation. That seems quite reasonable. But is there another way that we could have solved this problem that you maybe already know? Like, for instance, perhaps energy conservation, right? So let's just say that we start the body at equilibrium and we pull it, or it is at equilibrium, we pull it away a distance x, right? We know that the total energy initial, when we let it go, that body is going to go back, and at any other point, whoops, I didn't really mean to draw the body there, hold on. At any later point, the total energy must be conserved. Total mechanical energy must be conserved. So let's maybe compare compare these 2 points. The end point where x equals a to where x equals 0. Okay, so the total mechanical energy, is K plus U, or the total initial mechanical energy is Ki plus Ui. Total final mechanical energy is Kf plus Uf. This is stuff you should be able to do all on your own. And if I pull it away from rest to this position here and I let it go from rest, what is the initial kinetic energy? The initial kinetic energy is 0 because it's from rest. And what's the initial potential energy? It's the potential energy of a mass in a spring, right? 1/2 kx initial squared. I'm going to say kx initial. X initial is just a, right? The amplitude, where x initial is a. So that the potential energy of a mass on a spring is 1/2 kx squared. I believe you should know that. K final, we want to know, okay, how fast is it moving when it gets to this positions, right, back to equilibrium, when it has its maximum velocity. That's going to be what K final gives us. So that's going to be 1/2 m, I'll write V final squared. And the final potential energy, well, since x equals 0, the final potential energy is 1/2 kx final squared, which is 0, right? That's 0 because x equals 0. Or I could have just written xf equals 0. Energy is conserved, so therefore EI equals EF. So therefore 1/2 k x initial squared equals 1/2 m v final squared. And we're looking for the maximum velocity, that is v final. So therefore, solving for v final, we get dividing by m, k over m, square rooting, And what we get is that. VF equals square root of k over m x initial. How does that compare to, whoops, don't worry about all the writing here. How does that compare to what I had found already for Vmax? Vmax is a square root of k over m. Oh, yeah. Xi is equal to a, right? So that is square root of k over m times a. Check. By energy conservation, we get the same result. We better get the same result. Okay. Have a great day. Oh, wait, I forgot to say. You look at this and you say, oh, wait a second, but this is a vertical mass spring. Shouldn't the potential energy also equal, shouldn't the potential energy also have an MGH? MGH initial and MGH final. And the answer is something that we've already talked about. This is really, really important because you are right. It should have an MGH initial and MGH final if X initial is measured from the unstretched position. And if X final is measured from the unstretched position, then it should be, the potential energy should be 1/2 k x squared plus mgh. But if we reset our position, just like we talked about before, such that we're measuring from the new equilibrium position that is given by the fact that it's hanging in a gravitational field, then we basically, or really, gravity is absorbed by the 1/2 kx squared function. That's the best way I can put it without writing out the mathematical equations. And you can prove to yourself that 1/2 k x squared plus mgh is equal to 1/2 k x nu squared. You can prove that to yourself, where x nu equals x unstretched plus the amount that it is stretched by gravity. So you can prove that for yourself. I'm not going to bother proving that, but you can prove that that is true. 1/2 kx squared plus mgh is equal to 1/2 k x nu squared, where x nu is the x unstretched plus delta x stretched by gravity. Hence, we don't use mgh because it's already absorbed, built into the 1/2 kx squared term. I know it seems a little strange, but it is absolutely true. You can do the math out for yourself and show yourself that's true.